Good afternoon and welcome to today's global webinar. Today's topic we'll be looking at electromechanical design for today's engineers. I'm delighted to have as your speakers today, we have Chad Jackson, who's the President of Lifecycle Insights, and from Siemens we have Kevin Moran, who's a Senior Application Engineer, Global Technical Business Development for Solid Edge. I will give very brief bios. We've got quite a packed program, and then we'll get things underway. Chad is an analyst, researcher, and blogger, providing insights on technologies used to enable engineers. He's a prolific writer and has published educational thought leadership topics hundreds of times. As a sought-after speaker, he has presented dozens of times, both domestically and internationally. And as an astute researcher, he has surveyed thousands of engineering organizations as part of his research studies. And in terms of a common sense approach, he's co-hosted numerous web shows and has debated and pushed the limits on critical issues around engineering. Okay, and after Chad's presentation, we have Kevin. Kevin joined the Global Technical Enablement Team in 2018 as a primary objective of focusing on the new Solid Edge Electrical and Solid Edge PCB products. Kevin has been involved in design, engineering, manufacturing for the past 20 years, and in one way or another, having spent over 12 years in the CAD reseller channels as a pre-sales engineer. That's 10 years of SolidWorks and 2 years at working Solid Edge. Okay, now that we have the bios over with, I'm delighted to hand over to our first speaker today, Mr. Chad Jackson.
Inviting me to participate today. This is a topic that I am passionate about. This is part of, I kind of see this as part of a bigger transition that many companies are making, going from traditional mechanical products to smart connected ones. So there's a lot of complications that come along with that, and what we're talking about today, kind of the collaboration between electrical and mechanical engineers on the development of electrical systems, is an area where companies can improve. So let me give you an idea of what I'm going to be covering in my part of this presentation today. First off, I want to talk about what's really driving a lot of these changes. There's a lot going on in the industry. There's a lot that is driving companies to kind of change the way they're developing products. So let's talk about that first. Next, we're going to talk about improvement opportunities. There are many of which executives can select or pursue. We'll talk about some of those options, and we'll focus in on a couple here today. Then we're going to talk about the established approach of executing that part of development, and we're going to contrast it with the novel approach. So there's a new way that you can develop these electrical systems and have mechanical and electrical engineers collaborate together, and there are some broader implications in terms of processes and timing and hitting design release. After that, we'll do a quick recap, and then I will pass it off to Kevin Moran, who will give you some insight into how Siemens PLM and Solid Edge can be used to address these issues that I'll be covering over the next 20, 25 minutes. So with that, let's go ahead and get started. We're going to focus first on kind of the business perspective here. So let's dive into that. So I think a lot of people recognize the fact that today the IoT movement is changing many products, right? So there is an increasing demand for smart products and connected products. By the way, we have a speaker. If you could mute yourself, that'd be awesome. So the challenge here is that there's a demand for smart and connected features in today's products, and that is driving a fundamental change in the composition of modern products. So you're seeing more electronics, and that comes in the form of antennas, sensors, actuated components, and ECUs with board systems and embedded software in them. And of course, they are all connected to one another through electrical systems. So the shift has been moving more and more towards electronics and software, especially when you look at innovation. Now, that is forcing a lot of companies to add competencies in those engineering domains under their own roof. You know, many companies for many, many years have outsourced a lot of that work. They've partnered with suppliers to provide that expertise in those different engineering domains, but I'm seeing more and more companies realize that, you know, kind of the development of software and electronics, that's becoming more core to the differentiators of their products. So they want to bring that in-house. And mainly because so they can have engineers work more closely together. So overall, that is resulting in, I guess the closest word I would use is called churn. There's a lot of churn in product development today as you bring on those competencies, there are implications on your product development process. You know, suddenly you're going to have new checks, you're going to have new milestones, you're going to have to do integration tests across engineering domains that you perhaps had not quite done before, or maybe done in this way. So there is change on this front. So this is one aspect of what is driving companies to change their development process. Another aspect is this, that there is still no give in the schedule, right? So if you look at competitive pressures, that is still driving many companies to keep the same schedules or even shorten them in delivery or launch, right? So that is significant. So things have gotten more complicated with the composition of products changing, and now, you know, many executives are realizing that there's no give to accommodate those changes. Time to integration test is crucial here. So if you look at software, getting embedded software to run on target electronic hardware is a huge challenge. You know, I think a lot of us recognize, hey, when you install a new software onto your desktop or your laptop, you know, making sure that runs, software developers go through a tremendous amount of work to make sure that works seamlessly early. Now, if you can imagine getting embedded software that's new to the world, running on electronics hardware that is new to the world, that is a significant challenge, right? So what a lot of companies are doing is they're trying to accelerate their pace to get to physical integration tests as soon as possible. Now, many companies are looking at model-based software development, which is what MBSD is. So this is the concept of using model in the loop, software in the loop, hardware in the loop. So basically connecting, you know, basically digital representations of the software or the physical side of your product to one another to verify that the logic runs as expected. However, this does not help organizations ensure that embedded software will run on target electronic hardware. So that is a good practice, make no mistake about it. However, it doesn't address this need to get software to run on electronic hardware as you intend. So, as a result, a lot of executives are further compressing development. They're moving milestones up because they want to get to that physical integration test as soon as possible. So, the other aspect to keep in mind here is electrical systems lie on the critical path. You cannot run a physical integration test without connecting multiple ECUs and sensors and actuated components together without the wires that connect them. So that is why electrical systems, along with all the development of all these other aspects of the product, are crucial. They all need to be compressed, not one or the other. Now, another facet of this challenge is that each of these pieces of the product are getting more complex in and of themselves. So if you just look at, for example, regulations on electrical systems, let's just look at aerospace and defense real quick. There's new regulations that demand not only redundant signals being sent between the cockpit and, say, the power systems and other types of systems, but there are also new regulations that require them to be routed through different sections of the plane, and also that they cannot be routed through compartments where fuel systems are also exist, right? So what's interesting about this is that checking those design rules to check compliance with that regulation demands a combination of logical information about the electrical system and physical information about that electrical system, right? So you cannot just work in a schematic, you cannot just work in 3D assembly and route your wires. You need both, right? So that presents some interesting challenges. In addition to that, I think everybody will recognize that, you know, as you're getting more electronics into these products, packaging that electronics and then also routing the electrical systems through those products is extremely challenging. So I think we've talked a lot about challenges, right? So I think we all know things are getting more complex and more difficult. Engineering executives and leaders are looking at different opportunities or initiatives that they could pursue to address these problems, right? So you'll see a number of these coming up on the screen. So system engineering, this is a way of, you know, breaking down requirements, defining functions, developing a logical architecture, and then a physical architecture, and having allocations between them. Using that methodology is great at mitigating risk due to the complexity of modern products. It's a great practice. Another thing that can be pursued is generative design for electrical systems. So this is the idea of automatically, you know, either developing traces or even, you know, on the electrical system side, developing the right connections between components. That's another option. A different one is modularity and platform development, right? So this is a way of offering more options for your products, yet reducing the complexity, the development complexity of your products. And finally, the last two that we're actually going to be focusing on today is collaboration between electrical and mechanical engineers, as well as simulation of signal and power integrity prior to prototyping. So let's talk about each of those in turn. So when we talk about collaboration between mechanical and electrical engineers, it initially starts with this. You start with the electrical schematic. You're passing a net list and a parts list to the mechanical engineer so that they can route wires through their 3D assembly. Those are the different aspects of the design within which they need to collaborate. Now, I think we all recognize that engineering is not a first pass type of process. It is iterative, right? There will be changes that will need to be made to accommodate all sorts of issues, right? That's the nature, the inherent nature of development. So the trick is, how do you pass and share changes back and forth? The other aspect that we're going to be looking at is looking at signal and power integrity. So when you pass a signal down a wire from one electrical component to another, due to the resistance in that wire, that signal would become weaker and weaker the further it has to go, right? So the outstanding question is when the signal reaches the other end of the wire, is it still strong enough to be read by that electrical component, right? So checking that across all of your electrical systems, across every single wire in your product, is signal integrity analysis. Same is true of power, right? When you are sending power down a wire, is the power at the end of the cable strong enough to power the component that you're trying to make active, right? So checking both of these things is critical. Now, what is crucial about this is that checking that requires a combination of logical information from your schematic as well as the lengths of the wires within your 3D assembly, right? Because you need to know which signal is on which wire and how long that wire is. So that is why you need collaboration between the two domains to make sure everything's going to work out correctly. Now, the technology enabler here is ECAD and MCAD applications and how they work together. How do you pass information back and forth? Okay? So let's now talk about the established way of doing that and the novel way of doing that. So with a traditional technology enabler, basically what you do is you export net lists and part lists from the ECAD application and you import it into your MCAD application. Now from there it acts almost like a to-do list for the mechanical engineer. They take that information, they have from to information, what component you're going from, and what component you're going to for each cable or wire. You can then kind of tick off the list and go down one by one. Now, of course, we talked about how this is an iterative process, right? So the issue with this approach is that when the information is exported from the ECAD application again, and it's imported into the MCAD application again, the issue is that you see wholesale changes. You're not just seeing the things that changed, you're getting all the information again, right? And that causes the mechanical engineer to have to go through and analyze every single piece of information, which is time intensive, and it's very laborious, especially for engineers that are very, very busy and that have a lot of different responsibilities today. They're wearing a lot of different hats. So that process, if we look at it, you have the electrical schematic, you export information, you bring that into 3D assembly, and then you route the wires. If you make a change to the schematic, you get a new iteration of that, and of course you export again to get that into the MCAD application, and there really isn't tracking from one iteration to the next for the mechanical assembly. Now, the implications of this on the process is that there's a lot of delay. Because this process is extremely manual, it's labor intensive, and you need to really assess every single wire for changes. Frankly, electrical and mechanical engineers delay this process until very, very late in design and development. So that, if you think about it, in and of itself, delays everything we talked about earlier. You know, we talked about executives wanting to compress the development cycle and have things happen earlier so they can get to that physical integration, right? Here we're talking about now delaying it as long as possible until the design is no longer changing, right? So those two things run counter to one another. The process here is similar to what we just talked about, right? We're exporting information, we're importing into MCAD, but when you get to that next iteration of the schematic, what often happens is that information is not exported and imported, and that means your wiring in the 3D assembly is out of date. That's delayed again and again throughout development and design until you get very close to the end when the information is exported and you go through this massive effort to update everything. Now let's talk about the progressive way to do this, or the novel way to do this. The progressive technology enabler here are integrated pairs of MCAD and ECAD applications. This allows them to be associative. And what that means is you can pass changes or propagate changes back and forth in an automated fashion, right? So the information is being communicated between the applications. There is no external file that is exported and then imported, right? This happens behind the scenes for you, right? So the manual effort is dramatically reduced. But in addition to that, the individual changes to wires are listed for you. And as you select them, it highlights the change in your 3D assembly or in your schematic, right? So you're automatically being almost notified of what the change. You have visual cues as to what to look for in the design. So this effort looks a little bit more like this. You have the schematic, you have the 3D assembly, you see an exchange of information directly between these applications. You can have changes to each of them, right, independent of one another, and when you get to those versions, they exchange information again, right? So this is automated. It's eliminating human error. It's eliminating the manual effort of the electrical engineer and mechanical engineer, even of, hey, let's even check, right? Okay, I have to export and import, right? So you're removing that as well. Now, let's talk about the implications on the process. And there are several. So first off, this allows early and continuous collaboration between the electrical engineer and mechanical engineer because the effort is reduced so much. It allows you to verify that everything works early on as opposed to waiting very, very late in the process. And finally, you're eliminating human error from reviewing those changes manually. You're being prompted with accurate information right up front. So this process looks very different, right? So you collaborate early, you share information back and forth, you can have changes in each of these representations, and those can be synchronized. You're seeing associativity, pass changes back and forth, and this continues early and continuously throughout the design process. Now, we've talked about kind of the collaboration and getting on the same page for electrical and mechanical engineers. There's another aspect here that we should talk about. Interactive highlighting is another capability that is enabled by these integrated pairs of mechanical and electrical applications. So the idea here is that you can be in the electrical application, the ECAD application, and select a wire. That will automatically highlight the corresponding wire in your MCAD application, right? Same thing happens in the MCAD application. You can select a wire there, and it will highlight in your schematic. Back and forth, back and forth, back and forth, okay? So this is pretty powerful stuff when you start thinking about the changes that you can have in your process, specifically real-time co-design. There will be, and I'm sure many of you have experienced this before, there are issues where you have to sit down or you have to talk. You might not be in the same office. You have to have a conversation between an electrical engineer and a mechanical engineer to work through competing requirements and competing issues or constraints. So the idea here is you can jump on a conference call. You can each be working in your own environment. You can each be working, the mechanical engineer is working in the MCAD application, the electrical engineer is working in the ECAD application. And they can go back and forth selecting wires, unambiguously communicating what wire they are talking about in turn, and propose different solutions for whatever issue they're facing, the competing constraints and requirements. So this is almost a new type of activity that can take place. Now, I want to step back for 1 second. One issue that we did not talk about here is that synchronizing the representation between the ECAD and the MCAD application also allows you to do signal and power integrity analyses early and often. If you remember, you have to have logical information about which signal is on which wire, and you have to know how long that wire is. Well, if you're syncing early and continuously throughout the process, you have that information at hand all the time, right? So suddenly you can assess that early and continuously throughout the design process. Okay, so this happens, and that's in a stark contrast with the other process, right, where we have, here we go, this is the image that I wanted to get to, where we're waiting until the very end to have an accurate representation of the routing through the 3D assembly. And in this case, you don't have accurate wire lengths until the very end, which means any analysis you do on signal and power integrity is inherently flawed and incorrect. So there are lots of implications when you look at the processes, when you look at the capabilities that enable these process changes. So let's recap. We've covered a lot today. So first off, there are many different competing pressures that are driving executives to compress the overall development cycle. I think we saw that earlier. Demand for more intelligent features, demand for more connected features. Everything is getting more complex, yet executives are trying to get to those integration tests as soon as possible. There are many different initiatives that an executive could pursue. One of those is improving collaboration between electrical and mechanical engineers, and the other thing is performing signal and power integrity analysis early and continuously in the design process. The established approach and kind of the traditional technology enabler relies on exports and imports between MCAD and ECAD applications. The implication on the process there, the unintended consequence, is that engineers wait until the very end to exchange information. And that means you're waiting to confirm a whole bunch of design rule checks. You're waiting to perform signal and power integrity analyses until the very end, right before prototyping and test. And that leaves you very little room to make broader changes. The novel approach relies on progressive technology enablers, which is an integrated pair of ECAD and MCAD applications that communicate changes in an automated fashion back and forth. They're synchronizing. And that means that these engineers can collaborate early and often throughout the process, and that allows them to make sure that they're on the same page with the design, to confirm or validate design rule checks, and to perform signal and power integrity analyses throughout the process. So that concludes my part of the presentation. Next up, we're going to have Kevin Moran cover how Siemens PLM and Solid Edge solution addresses these needs. Thank you again very much for allowing me to participate.
And thanks, Chad, for your kind of introduction and background on this sector. So my name is Kevin Moran. I'm a Senior Applications Engineer in the Global Technical Business Department for Siemens Solid Edge. And today I'm going to take you through an introduction to the new Solid Edge electrical design software that we released into the portfolio for Solid Edge 2019. Okay. So for manufacturers to meet market demands and maintain the level of quality their customers expect, they need to understand how best to integrate the mechanical, electrical, and electronic aspects of their designs. With this in mind, I introduced the new Solid Edge electrical design software, a suite of applications developed to satisfy the requirements of companies where ease of use and value are as important as functionality. Solid Edge electrical design consists of two main elements: the wiring design and harness design applications. Solid Edge wiring design provides electrical wiring circuit design and verification tools for the rapid creation of wiring diagrams and the verification of electrical systems. Solid Edge wiring design is an electrically aware schematic tool for designing the wiring of electrical systems for multiple industries that could include industrial machinery, specialist vehicles, consumer devices, or medical equipment. It comes with a built-in verification and design rule check to ensure that products are optimized for their performance and reliability. Its intelligent parts libraries help drive the design process with automatic part selection. As part of the Solid Edge family, the connected mode allows dynamic ECAD and MCAD collaboration with cross-probing and dynamic updating between mechanical and electrical domains. We're also introduced Solid Edge harness design, With rapid and intuitive wire harness design tools, together with automated part selection, design validation, and manufacturing report generation. Solid Edge Harness Design is the best-in-class wire harness design application for in-house design of electrical wiring harnesses and the creation of information required to manufacture the harness. You can design harnesses standalone or derived from the wiring from the Solid Edge wiring design module. Connected phase views and tables make it easy for designers to determine how wires terminate, and the intelligent part library drives the auto-selection of terminals, seals, and wires. Solid Edge Harness Design integrates closely with Solid Edge for routing efficiently around a mechanical assembly. This allows our customers to quickly and confidently bring electromechanical products to the marketplace. So let's now take a look at Solid Edge electrical design in action. So in a world of ever-increasing electrical complexity, being able to accurately document and design an entire product has become a serious challenge. Previously used unintelligent drawing tools and spreadsheets are no longer capable of keeping track of the electrics in product designs. Companies have a strong need for a smart electrical design environment, one which can validate and provide automation as design processes progress. Finally, it is essential for electrical and mechanical teams to collaborate early in order to reserve space and trap issues prior to production. So I introduced you Solid Edge Electrical Design. Solid Edge Electrical Design answers the need for advanced wiring capabilities and forward design with two unique offerings. First, Solid Edge Wiring Design. Solid Edge Wiring Design supports multiple industry sectors, so whether you design machines with three-phase routed connections, where you need to bend, fold, and add chamfered connections to show wire routes, or vehicles with specific drawing standards, Solid Edge Wiring can help. An intuitive user interface and intelligent library of parts, which automatically selects parts as you proceed, provide intuitive workflows for things like harness connector selection. Next, Solid Edge Harness Design. Solid Edge Harness Design allows for the creation of scaled and full-size form board designs. Everything required to design and manufacture a harness is available from clips, grommets, insulation coverings, to less common components such as seals and plugs. Harness processing tasks such as terminal part selection and wire length adjustment based on the selected connector can all be automated. Solid Edge Electrical Design provides the essentials that product designers and manufacturers need. It also electrically validates circuits using built-in dynamic analysis, qualitative analysis for checking the circuit for correctness, and numerical analysis for dynamically indicating any voltage drops or load issues. It's easy to see how Solid Edge's line of electrical products can increase precision and productivity in anyone's workflow. We'll take a look at a working example. We're going to look at how we can leverage the connected mode between Solid Edge wiring and Solid Edge electrical routing when making a seamless workflow between the 3D models and the electrical schematics being used in the design harness. As you can see, a majority of the harness has already been created for the torque tester unit. However, we still have a few components to finish up before the harness can be fully validated and ready for the form board. Connected mode creates a link between Solid Edge Electrical Design and Solid Edge Electrical Routing to exchange data without the need for file imports or exports. Connected mode can work either on the same or local machine system or remote computers, allowing electrical engineers in charge of the schematics to easily link up and work with the mechanical designers in charge of the designs. Once linked, the cross-highlighting option will allow for bi-directional highlights of any components associated to the schematic. This capability ensures precision when working in two separate environments. To finish up our design, we need to add a few more wires between the control board and an output connector. As the components have already been placed and identified, creating the connecting wires is as easy as selecting the pins we want to route from and defining the pins we want to route to. Next, we'll identify the types of wire, color, thickness, and turn on the display of the wire lengths. Wire lengths are critical in ensuring a proper simulation of the harness, and we'll show you how using the Solid Edge electrical routing, bringing the true wire lengths back into the Solid Edge wiring design is as easy as a click of a button. Finally, we need to associate the newly created wires to the appropriate harness, and the schematic is complete. With workflows like this, creating and managing wire harness designs is easy and intuitive. With the wires created, now it's time to make it real in the 3D design. Using filters to manage which schematic data we want to send across, pass along the information as simple as clicking the bridge out command. Once bridged, Solid Edge alerts us that an update has come across and ready to be routed. Zooming on the PCB, we see the 4 spade connectors that the wires will be routed from. Solid Edge Electrical Connected mode ensures all the information, such as component IDs, names, and descriptions, are all passed across when bridged. If there had just been a single instance of the connector, Solid Edge would have automatically linked it back to the schematic. But as there are 4, and all are essentially the same part, we need to identify which occurrence is which. Once everything is defined, Solid Edge interrogates the model and cross-references both the test stand and the control cabinet harness to ensure that the components and connectors are as they should be. If we were to delete a wire out of the schematic in Solid Edge wiring design, that wire would also be deleted out of the Solid Edge harness. Now, as our only change are adding 4 wires, Solid Edge quickly generates and connects them to associated component terminals in the design. From here, we'll just simply use the Solid Edge wiring and routing tools to bundle the new wires into the existing harness. So using the predefined paths we already have in place, we can just quickly select the wires we want to bundle, choose the path that we want to bundle them through, and then watch as Solid Edge does the rest. We'll notice that the wire colours are different from those that are already being used on the connectors. So to make some changes, we'll go back to the Solid Edge electrical design, open up the properties, and we can quickly change the colours of the wires to an appropriate colour to match the existing wires inside the harness. As simple as that, we can click on the bridge out, send the information back into Solid Edge, an update's available for us, and just by updating the design, we can see that the colour of the wires have now kind of matched. So once everything is routed and in place and we're happy, we can bridge all of the information back into Solid Edge wiring design to get accurate wire lengths and validate our wire sizes are appropriate for their lengths. So Solid Edge's new electrical design and routing capabilities continue to push the boundaries, providing our customers greater accuracy and efficiency when designing their everyday parts. From using Solid Edge wiring designs to create, edit, and validate harnesses, Solid Edge electrical routing to easily validate, visualize, and find accurate wire lengths, through to Solid Edge harness design to create accurate formboard prints, identifying exactly how the harnesses are physically created. It's easy to see how the Solid Edge line of electrical products can increase precision and productivity in anyone's workflow. So in summary, the Solid Edge electrical design software modules cover all of the needs for designing and simulating electrical systems and manufacturing wire harnesses. Solid Edge electrical design software can validate your design and generate all of the supporting manufacturing documentation you will need to complete the job. This will enhance your time to market, enhance your product quality, and greatly improve your profitability. So with Solid Edge electrical design, you get your design right first time. For more information on Solid Edge electrical design, please click on the link in the WebEx portal that Jay has posted. Thank you for your attention.
So it just remains for me to say thank you to our panel, Chad Jackson and of course Kevin Moran. And again, apologies for any loss of audio to any of our attendees. And of course, thank you to you all. With that, the session is closed. Goodbye.